Yes, yes, fine. Good evening. Give me 5 minutes. I am sharing my screen.
Okay, brother.
If you want, you can record the session. And we are starting with the 14 bus system. And then we'll check the major project, capstone project of the offshore HVDC system. So, have you started the recording? Can we discuss? Okay. So, this is the 14 bus system project in which 14 bus are there. And as per your requirement, we have used one wind generator and we have used one battery also. Okay. So this is a battery energy storage system, BESS, look like this way. And this is a wind system. And let's start with the exact what is actually the 14 bus system has three major buses. One is our swing buses, then PV buses, and then PQ buses. Okay, so here we have used different buses as per uh, requirement. So the all the PQ are load. If you can say PQ load, which means that the bus is treated as a load. Load means electrical. You can say area or you can say industry. So this is the load, and active and reactive power is mentioned over there, P and Q. That's why it's called as a PQ load. And if you want to check, you can go load flow session and you can see constant PQ. Then this is a PQ generator. There is a two generator. One is PV generator, one is PQ generator. PV generator help to maintain active and reactive power inside the system, whereas PQ generator is do nothing. It's just doing whatever the active and reactive power is mentioned over there. Let's say this is a PQ generator and active and reactive power is mentioned over that. Irrespective of requirement, the generator power, active and reactive generator power directly fed inside the system through this PQ generator. PQ generator are mostly used in blackout condition whenever uh, why we are using it, because if you know grid means numbers of power plants are connected together to one single, I can say, to interconnected grid. So this is a power plant A, B, C, D connected, all connected together. This is the power plant X at which you are working over there. So let's say you are feeding power through this main breaker, main switch to your power plant. Let's say you have PV generator, you have PQ generator. PV generator are always trying to generate same voltage and same frequency offered by grid. Obviously, we have to follow the grid. We have to follow the grid compliance grid code. So whatever the voltage is there, whatever the frequency over there, that is followed by this PV generator. Whereas PQ generator is just doing nothing. It's generate the power. If power is extra, it is feeding to the grid, or the remaining power is used by auxiliary system. If you are working in the, like, auxiliary means, if you are working in the thermal power plant, you run boiler, you have to run pumps, electrical motors, so that are auxiliary load, and that is fed by this PQ generator. So at that condition, if some abnormality happen and you disconnected from the grid, this breaker is tripped, isolation. At that condition, PV generator are isolated, but PQ generator remain in the picture and control and supply power to the entire power plant, entire necessary load. So this is the importance of the PQ generator. You can consider as a backup generator also, or DG generator also. So mostly you are in swing buses, PV buses and PQ buses. Swing buses means grid. This is the reference. Grid has some voltage and some frequency, and that we have to follow. That all the generator are follow. The generator, PV generator, PQ generator, all generator follow voltage and frequency of the swing generator. So this is the swing generator. You can say this is a main reference, and all all generators. What I can say, whether it is a PV generator or PQ generator, they are trying to maintain the voltage level offered by this main swing generator. Okay, so different buses are there, different interconnection are there. Each line has some resistance and reactance part. Mostly you can change as per your convenience, but make sure it's lower. If you increase high value, that may cause a voltage drop. And all the generator are 11 kV, and all the buses are 415 voltage. And you can say, as per your requirement, I have prepared the SLD also. I have SLD and I have AutoCAD drawing also, but I think SLD is okay for you. So whatever the generator, battery system, wind power system, and the interconnection are mentioned over here, similar to your exit connection. Okay. And hmm, okay, this is the bus which is connected to the battery energy storage system. So this is the battery on off. You can just on off the battery. Actually, this is a charge for measurement, and it's not required right now. Okay. By just turning on and off the switch, you can control like whether battery is charged or battery is discharged. So this is a switch. You can change the duty cycle, which eventually change the, what I can say, eventually change the duty cycle of these MOSFETs, and whether it shall be a generator power or not. Okay. So mm, mm. And then this is a DC to DC converter which is connected with the system. This is a VSC controller, and that used to synchronize the power generated by DC power generated by battery, convert DC power into three-phase AC power, and synchronize with the grid. And you can see it is directly connected to this bus. Then this is a wind system, and 13 kilowatt wind turbine we have used. And this is just a simple logic. Initially, if the voltage is lower, so how wind is generating? Wind turbine takes some time to rotate and reach some voltage level. So your voltage is exponentially increase, and then it is stabilized like this way. So this voltage may be a 700 or 800 as per our requirement, and you can convert into 450. This is a DC voltage. So this is the time. You may 0. In simulation you may face 0.2 to 0.5 second, but in practical that may be a 10 to 20 minutes also, because wind start rotate, turbine start rotate, then generate power, generator rotates. So it's time consuming activity. So you have to consider from zero, and that's why it takes some time. And initially the voltage is lower. So if you just run the model, you have to wait for more amount of time. So we have just created the logic. We are measuring the output voltage directly from here, and if it is lower, as per our requirement, we are feeding high input, 50 meter per second as the wind speed. And once it reaches 780 or greater than 780, we are switch back to the 20 meter per second, which is a normal speed. And this is not practically used to fast the simulation and to reach the voltage level as quickly as possible. We have used this type of logic. There is no such any use in the practical way. You can see this is a no wind situation is also there. You just double click on the switch, zero input, so there is no generation. There is no wind, there is no generation. Wind turbine and permanent magnet synchronous generator. Wind turbine kilowatt you can mention over there 15 kilowatt. Okay. So and the generator, if you convert this to the kilowatt, you will get nearly 13 kilowatt. Then this generation three phase AC supply generated by the generator. We have converted into DC supply, and then we are controlling the voltage. If the voltage is proper, then and then this breaker is on, otherwise not. Then the battery just to store the extra energy as a backup source and to maintain the stabilized input at the initial stage. And then it is connected to the inverter again. DC supply is connected with the inverter and eventually connect to the system. Before you run the model, make sure you have to paste this code in command window. You can see the variable are defined, and now you can run the model. Before we run the model, let's first run the load flow analysis, because our major concern is load flow analysis. Double click on this block. Hope you understand. Extremely sorry I did not ask you anything. Do you have any question till now? Just go through the model. Initially, you may face some issue, but just go through, just understand the component level. And if you in between face any issue, just text me. I definitely reply. No issue. So this is a load flow analysis, the actual use of load flow analysis to measure the voltage, current, voltage, voltage angle, active power and reactive power at different bus. P, Q, V, delta. Take some time and you will see some pop-up of the load flow table. So you can see all the buses that we have used. All the 14 buses are mentioned over here. The voltage level is also there. It is coming a 240 kV, means 230 single phase supply, 450 three phase supply. This is what we are going to measure. Right now it is 0000. You can change the unit, kilowatt, megawatt, kVA. Just press this compute button and then it start calculation, and then eventually it giving some output, which is a voltage angle, P and Q, active power and reactive power. Again, we need to wait. It's not directly coming. Yes. After some calculation, you can see what we are getting. So bus one, then this is the bus as a reference bus, swing bus. That's why it is zero. Whereas remaining are the voltage are in limit, which is coming one. The angle is also nearly active power and reactive power. We are taking this much amount of active power from the grid, from the swing generator, which is the reactive power. Then if you, I have mentioned one PQ generator, which is just feeding whatever they are generating. So you can see 1 kilowatt and 500, or I can say 5 MVA. So it's which bus? Bus number 8. Just find bus number 8. Okay, this one generator 5 is a PQ generator. You can see 1 kilowatt and 500 kVA. So it's not a MVA, it's a kVA, it's a MATLAB error. Even though I am changing the units now, it's just remain MVA. If I am going into watt, then you can see it's MVA. So when I am in the kVAR or KVA, showing the MVA, but actually it is a kVA. So the 500. Then different generators. Let's say what is generated by the battery and the okay subsystem BSS system. Battery is feeding the power 20 kVA inside the system, and wind is also there. Subsystem wind, which is feeding back the power 22. And the remaining load, if you check the load, this is a bus number 10, and if you can check, bus number 10 has a 10 kilowatt of active power requirement and 1.5 kVA reactive power requirement that you can cross verify. Just find the bus number 10 and you can see 10 kilowatt active power requirement. And if you average out, how you can average out? Obviously 1.5. So if you capacitance will remove the effect of inductance. So that's why it come 1500, 200, 2000 minus 500. So it's coming 1.5, 1.5 kVA, 1500 watt. Okay. Actually, it is in watt, VAR, and we have kVA. That's why. So this is what you can cross verify the load flow analysis inside the system. In next step, we can add one fault also, three-phase fault. Actually, I forgot about it. Three-phase fault you can add and just do the fault analysis as per your requirement. So you just add a three-phase fault inside the system and you can perform the fault analysis also. Let's say we wanted to create a three-phase fault at particular this location. And okay, so make sure this switch must be off condition. And if you run the model, you can just on and off within few seconds. So you can see how your system is going to respond against the fault. The fault analysis is also covered. You can see the model is started, and if you want to check the waveforms, initially it takes some time to stabilize, but yes, takes some time due to the battery and the different sources that we have used. But after some time, it is clear and stable. Initially, it takes some time, and then you can create the fault. You just turning on the switch and turning off the switch. You are creating the three-phase fault on the transmission line, and you can see the influence of it on the different load condition. So the fault is nearer to this buses. You may check more influence. That is, if it is a too much isolated, like this bus is isolated from it, so you may face very lower influence or sometimes negligible influence of the fault over these buses. If you create the fault near to these buses, obviously it's coming more over here. So it's totally depend on at which location you are going to create the fault. So this is what the voltage and current that we have generated, and take some time to stabilize. What about the load? And what about the source, like a battery and the solar generation? Sorry, the generation. Due to this synchronization, this type of frequencies are coming. And this is what generated by the battery. And you can see the switch is on, and you can see the battery is right now charging. So negative ampere means battery is going to charge. Positive ampere means battery is going to discharge. As I turn off this switch, it means that right now battery is going to discharge and feeding power back to the grid, back to the system. Initially, it was taking power, but as I have changed, yes, it takes some time to stabilize. After some time, the battery ampere will uh, coming positive. And let's create the fault. Just create the fault and isolate the within a few seconds. And let's check what is the influence of the fault, whether it is detected or not. Okay, there's no major influence. If I turn on the fault, okay, it's far more location. That's why there is no major influence. But yes, there is influence. The current is increased. You can see the current is increased and the waveform quality is also changed. Initially was more stable, but as the fault happened, the current waveforms change, and this type of variation are coming due to the synchronization mismatch with this non-renewable or renewable sources. You can see the influence as the fault occur. It influence on the battery and influence maybe influence on the wind also. You can see the influence. So this is how you can create the fault and analyze. You want to just take a pure sine wave, just take the screenshot over here. Don't take entire screenshot. Otherwise, you may say, or your professor may say, why it's not coming pure sine wave. But actually, it is sine wave. Due to the synchronization, we are synchronizing with the grid through the VSC controller. Takes more time to synchronize. That's why. And you can see after the fold, the waveforms are totally malicious. And this is what the influence of the fold. And that's why the fold must not happen inside the system. For the remaining location, let's say this location, there was no major impact of the fold. There is, but not that much. You can see. The waveform quality is totally malicious after the fault. Initially, there was a clear sine wave. Even at this condition, you are seeing clear sine wave. But right now, it is not due to the influence of the fault. Okay, clear? Mm, not understand. What happened to the generator? So at this condition, we have created a fault over the transmission line. So if the transmission line has a fault, you can see the influence are coming. And the influence is more due to the due to these converters, due to these VHC converters. And it take more time to stabilize. But if the generator is totally fail or if grid is totally fail, so this generator must not fail. It's a swing generator. So all the load are coming over there. But if this generator failed, you may face some more power consumed from this swing generator. But yes, there is no major impact. The major impact is coming when this grid fail. If this generator is failed, then there is a major impact. If you want, we can add one breaker also. So you can just isolate the generator from the system and you can create whatever scenario you require. But if you isolate this grid, because every generator are trying to, I can very frankly say, कि maintain frequency and all things through this source. It's a swing source. And if you directly isolated it, na, that may cause instability inside your system. And let's add one breaker at the PQ generator also. So you can see how the system behave when one power plant is isolated. Let's add at this point also. Make sure initially the switch is on. Hmm. Okay, we have added, and you can say right now it is also generating power properly. And It wait for slight more time to stabilize. The influence of removing the source is that it increase the current of remaining source. Like if it's a swing source, it will take more power from the swing. Let's isolate it. So the breaker is right now off. So different. Okay. You can see the instability due to the isolation and for this generation. Yes. So whenever any source are coming or removing from the system now, what actually VSC converter is right now doing, VSC is taking reference. So if you are isolating any part, or if you are tripping any part, or if you are causing any fault inside the system, the sine wave quality are changes. As VSC controller depend on the sine wave quality. So if there any type of abnormality are coming or any type of switchings are happen, slight variation in the sine wave cause the instability in this VSC controller and that eventually cause the disturbance. You can see the disturbance are coming after the turning on and off. It will stabilize after some time, but yes, it is coming due to the instability. Let's just turning on the breaker again.